But now, like, carbonate's at, like, nice price.
Well, the Gators were kind of disappointing this weekend.
Kind of. Don't talk about it. Call me.
Let's not talk about it. I got so bored watching the Gator game, I switched over to the Lawrence Welk show. Anyway, here is a physics lesson, a practical physics lesson. It may help you someday. The downstairs air conditioner in my home died. I think it was like 20 years old, and so it died. And I had a band rehearsal on Sunday, and I had no AC. How do you solve that problem? You get 8 bags of ice in a wash tub, and you blow a fan over it. So it's like the random walk on steroids. Because the fan is shooting air, nitrogen and oxygen molecules into the ice. Bam, they hit the ice. They deliver all their kinetic energy to melting the ice. So when the air oxygen and nitrogen molecules come off, they're cold because they give up their energy to the ice, and you can cool a room this way. So I cooled my studio for a 3-hour band rehearsal with a tub of ice. I'll show you what it looked like afterwards. So the interesting thing is that the ice is like an inverse fuel. It's like an inverse fuel. So afterwards you can see all the ice is melted almost, and it's mostly water. So the ice is an inverse fuel. It sucks heat out of the air, and the air that bounces off the ice is cold. There you go. All right, now, but that's not what we're here to talk about. Let me say that we got, I think the exam 1 scores are posted, I think, and the average in terms of percent was 74, which from my perspective is just about perfect. Not too high, not too low. So, successful, at least from my point of view. I will add, however, that exam 1 is always the easiest exam. Because exam 1 is basically review stuff. And it's not till we get to exam 2 that we start really focusing on a bunch of new material. So you did great on exam 1, don't get complacent. Exam 1 is always the easiest one. All right. So, but good job. Very happy with that. And what it proves is that I taught you something. Because I'm sure that if you took exam 1 before you took this course, the average wouldn't be 74, right? So I taught you something, or you learned something in spite of me, one or the other, I don't know. Either way, you learned something, and that's good. All right, last time we went in infinite and ugly detail about how to calculate the pH of a solution of a weak acid. Now, as I said, that sounds like an arcane calculation, but if you're involved in any kind of research in aqueous solutions, and that would be all of biology and all of biochemistry, knowing the pH of your solution is important. You got some sort of bacterial culture growing. If the pH gets too high, the pH gets too low, they all die. And so knowing the pH, knowing how to calculate pH is something that people who have scientific/technical careers should know how to do. So we developed that in infinite and ugly detail. I want to talk today about polyprotic acids and how we're going to handle that. And then I want to do the same analysis that we did for weak acids with weak bases. So that's the agenda today. Now, polyprotic acids. Polyprotic means the acid has more than one proton that can dissociate. The quintessential example is our friend phosphoric acid. We know that phosphoric acid, you dissolve it in water, and it dissociates to a little bit and a little bit of that. Now, and we can describe that by a Ka. But now we're going to number them. Ka1, it's the equilibrium concentration of the hydronium ion. That's dihydrogen phosphate. Dihydrogen, there they are, 2 hydrogens, phosphate. And you remember, when I told you, you hear the suffix ate, 8, you think anion, divided by the equilibrium concentration of the phosphoric acid. And that, Ka, okay, what jumps out at you when you see that Ka? You go, whoa! It's a little high. Very good. We said the quintessential weak acid has a Ka around 10 to minus 5. So as weak acids go, this is on the strong side. But it's still a weak acid because obviously this is very much a reactant-favored reaction, nevertheless, because the equilibrium constant is less than 1. But as garden variety weak acids go, this is a little bit strong. Now, but that's not the end of the story. That dihydrogen phosphate can dissociate again if it wants to. And we call that hydrogen phosphate. Again, common story. We got the old ATE ending. And I'm not going to write out the Ka2. You can do it for yourself. But that Ka2 is 6.2 times 10 to minus 8. And then finally, the hydrogen phosphate can dissociate. What? Oh. I knew there was an H problem there, but I couldn't remember what it was. Thank you. What a maroon. So we can do that. And that Ka we call Ka3. And that is all right. So again, now we look at our numbers. We start off by going, whoa, that Ka1, that's kind of big. That's kind of a stronger side of a weak acid. That Ka2, on the other hand, is on the weaker side for a weak acid, because we said weak acids, garden variety weak acid, Ka around 10 to minus 5. Whoa, look at Ka3. That's a very, 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 very weak acid. All right, but what you notice, if you look at these numbers, is that Ka1 is much, much greater than Ka2, which is much, much greater than Ka3. And so this becomes very important to us when you're asked to calculate the pH of a solution of a polyprotic acid. You worry only about Ka1. So let me just write it out so we make sure, get it right. When asked to calculate the pH of a solution of a polyprotic weak acid, assume it is monoprotic so you assume it's monoprotic with Ka equal Ka1. So we don't have to worry about the second dissociation. We don't have to worry about the third dissociation. If the problem simply asks to calculate the pH of a solution of phosphoric acid, as it says up there, when asked to calculate the pH of a solution of a polyprotic weak acid, assume it is monoprotic with Ka equal Ka1. So that makes polyprotic acids essentially the calculation identical to monoprotic acids. All right, and I can assure you, you will be asked to do that calculation. Now, where am I? All right, so let's turn our attention now, as we said, to weak bases and see what we can learn about weak bases. So, one way to think about weak bases is the prototypical weak base would be our friend, we can draw it this way, ammonia. So there's our friend ammonia. It's a weak base because it has that lone pair. That lone pair can accept the proton from an acid and make the corresponding ammonium ion. But you can think of just tagging that NH2 group onto any molecule. You can think of tagging that NH2 group onto any molecule. So for example, you could take a methyl group and stick an amino group on it. And that's called methylamine. And just like that lone pair on the parent molecule ammonia makes it a base, the lone pair on that amine makes it a base. So there's primary amines like methylamine, and that Kb so we can say ammonia. Let's make a table here. Make a table. We got base and Kb. All right, so we talked about our friend. How many letters? 1, 2, 3, 4. Don't need to be that long. 1, 2, 3. What an idiot. Okay, that's terrible. All right, so now let's take our friend ammonia. We're going to put our friend ammonia right here. NH3, and that Kb is 1.8 times 10 to minus 5. So there you go. We said the garden variety weak acid had a Ka on the order of 10 minus 5. There's your garden variety weak base, Kb on the order of 10 to minus 5. So, start with our friend ammonia. Kb, garden variety Kb, 1.8 times 10 to minus 5. Then we can make methylamine. Still a weak acid. 4.4 times 10 to the minus 4. Little bit stronger. Let's make another interesting molecule here. So let's take our friend ammonia. This is what happens with a poorly drawn table. You have to basically redraw it. There we go. Not be. So you can see what we're doing in this series is in each case we're plucking a proton off of NH3. NH3 is the parent. Pluck a proton off, replace it by a methyl. Still a base, stronger. Pluck 2 protons off, replace by 2 methyls. Stronger still. And so this is ammonia. Methylamine. And this is dimethylamine. And you can carry this to any point. You can make this molecule. Here's a fun molecule. You can take our friend benzene. Benzene. Put a methyl group on benzene. That's called aniline. Kb equal. So much weaker. So you can see, starting with that parent molecule, ammonia down there, we can tag all kind of things onto it. We can tag a methyl onto it. We can tag 2 methyls onto it. We can tag a benzene ring on it. And all these things are bases, and their base strength varies with what's tagged on it. In this case, with aniline being a very weak base. Now, this base characteristic is seen in the medical profession. So here's a molecule that you take if you have allergies. It's antihistamine. And if you look on the label of this antihistamine, you'll see diphenylhydramine hydrochloride under the name Benadryl. And if you Google the chemical structure, you get this. What does that mean? Well, part of it's understandable. This is the chemical structure of the molecule. It's got 2 benzene rings. Again, what we talked about, you're going to need to know this for organic chemistry. Whenever you see an apex, that's a carbon atom, right? Now, is something missing from that carbon atom right there? Well, carbon has got to be tetravalent. You only see 3, right? So there's a hydrogen right there. Get used to this. This is how organic chemists work. Too lazy to put the hydrogen. What about this methyl? Got to have 2 hydrogens. What about that methyl? So again, I know it's a methyl because there's a bend there. I know there has to be 2 hydrogens because that would make that look like a divalent carbon, and there's no such thing. All right, so we can piece together the chemical formula okay. What's that bar represent right there? What's that represent? That represents a methyl group, CH3. Gotta know this stuff. So if there's nothing, it's a hydrogen. If it's a bar, it's a methyl. These are the rules. So this is now what's called a tertiary amine. Methylamine is a primary amine. Dimethylamine is a primary amine, secondary amine. This is a tertiary amine. Why is it a tertiary amine? Because all the protons are gone. That proton was replaced by a methyl. That proton was replaced by a methyl. That proton was replaced by a CH2, CH2. What's CH2, CH2 called? Methylene. Got to know these things. Take organic chemistry. So we can piece out the chemical structure of this molecule. There's only one thing that doesn't make sense. What's this HCl here hanging out in space? That HCl is very, very important, and since you all are going to be, many of you are going to be in the medical profession, I think you need to know this. This is called a hydrochloride. What is a hydrochloride and why do we make it? If you go and look at cough medicines and pharmaceutical products, antihistamines, hydrochlorides are everywhere. What does it mean? It means the parent molecule is the base that I show up here. Again, this is a tertiary amine. Everybody got this nomenclature? Ammonia. Take off one of the protons, primary amine. Take off two of the protons, secondary amine. Take off all three of the protons, tertiary amine. So that's the parent molecule. Now, the problem with that molecule is that it has low water solubility. And that is a showstopper for its use as a drug. You can take this drug orally, it doesn't dissolve in the bloodstream. That doesn't help you any. So hydrochlorides are made to increase the water solubility of a drug molecule. This drug molecule, look, one of the most important things you'll ever learn in chemistry, write it down. Like dissolves like. Like dissolves like. Very, very important. So you look at this end of the molecule, that doesn't look anything like water, does it? That doesn't look anything like water. That looks like oil. That looks like diesel fuel. But that doesn't look anything like water. It's hydrophobic, in fact. So like dissolves like. This is not going to be soluble in water because of this great big greasy set of benzene rings there. So what do? You want this molecule to be soluble in water because you want to sell it as a tablet. So what you do is you react that molecule with HCl. And this thing is a base. Yes? I don't know what that arrow's doing right there. You react this molecule, there it is, with HCl. The hydronium ion protonates it to make the ammonium chloride. That is a hydrochloride. So that's very water insoluble. That's what it is. This is a hydrochloride. It is very water soluble. So that's why we make hydrochlorides, because we want to take this drug molecule, which is water insoluble, and create it to a much more soluble form. It's a very important point to make. You tag a charged group on any molecule and you make it water soluble. Again, very important. If there is a charged group on a molecule, chances are that molecule will be water soluble. And so this is why hydrochlorides are made. And you see it, as I said, throughout the pharmaceutical industry. Something you should know. All right, now what? Oh, same thing with illegal drugs. This is cocaine. But again, you see great big hydrophobic mess here, not very water soluble. React with HCl, make cocaine hydrochloride, very water soluble. And then you've heard this thing called free basing. In fact, that goes back the other way. You take the proton off and regenerate the base. All right. So that's hydrochlorides. I think that's all I got on here. All right. Now, you will be asked to calculate the pH of a solution of a weak base. And I'm going to make it real easy on you, as I always like to do. Easy going Chuck, they call me. Somebody call me that, I'll hit them. All right. So, you will be asked on quiz 2, coming up, what a lovely thought, to calculate the pH of a solution of a weak base. How are we going to do that? Well, let's review what we did in the case of a weak acid and see if this helps us. So in the case of a weak acid, we could, if we wanted to, go right to the old ice table. And we could get a quadratic equation. We could solve that quadratic equation exactly. But we also said that what comes out of that ice table is that equation. So that's what comes out of the ice table. And last time we said if H plus is much, much less than the molarity of HA, this gets really simple, and we're left with this equation, H plus is equal to the square root of Ka molarity HA. So there, in a nutshell, is what we learned about weak acids. And I said, for me, I usually start here, check this assumption. If the assumption's good, I'm done. If not, I solve the quadratic equation. Now, we can do the exact same analysis for a solution of a weak base. So for a solution of a weak base, we can do the same thing. Solution of a weak base. We can, if we want to, go right to the ice table. What we will get from the ice table is a quadratic equation. We can solve that quadratic equation directly. But if you do that, what you will find out is here's the quadratic equation that you'll get. So I told you it would be really good just to remember this equation right here. And it gets doubly good because it's the same equation for a weak base, basically. H plus substitutes, or OH minus substitutes for H plus, and Kb substitutes for Ka, but it's the same deal. And then, just as in the weak acid case, if OH minus is much, much less than the molarity of the base, then you got the corresponding equation. OH minus is Kb molarity, square root of Kb times the molarity of base. So the weak acid case and the weak base case are identical. And the calculations are identical. So for me, all I do is remember that equation 2 up there, and I can take it from there. But if you don't want to do any of that, as point 1 says, the ice table will work also. So there are lots of ways to approach this problem, but the weak acid and the weak base, the ice table is the same, and the mathematics that you get pretty much the same. Okay, now let's talk about, okay, Gibby, let's talk about that. Right. Another point that's worth making. So what I've done here is I've drawn an analogy between weak acid and weak base. There's another important analogy that can be drawn between weak acids and weak bases. So what we're trying to do here is to tie things together to make things simpler. So let's take our friend ammonia, weak base. There's our friend ammonia. Our stinky friend ammonia. You put our stinky friend ammonia in the water. He's like our hippie friend, you know. And you get the conjugate acid, ammonium, and you get hydroxide. So there's our stinky friend ammonia. Put our stinky friend in water, we get a little bit of ammonium, a little bit of hydroxide. Now, we can write Kb. We know how to write that Kb. That Kb is the equilibrium concentration of the ammonium, the equilibrium concentration of the hydroxide, divided by the equilibrium concentration of ammonia. Now, but ammonium is our conjugate base, or our conjugate acid. It can act like an acid, man. So we can take our friend ammonium aqueous, and it's a weak acid, so it can dissociate into the hydronium ion back into the ammonia. So weak base acting as a weak base here, described by Kb1. Conjugate acid of that weak base down here, written as an acid dissociation, described by Ka. Described by Ka, and we can write Ka in this case is the equilibrium concentration of hydronium ion, the equilibrium concentration of the ammonia, and the equilibrium concentration of the ammonium. Now, here's the punchline. Ka, for any conjugate acid-base pair, Ka times Kb is equal to Kw. So you can show that for yourself. Just multiply the expression for Ka times the expression for Kb, and you get Kw, because in this case, okay, so in this case, we take Ka times Kb. That's equal to our Ka, H plus NH3, ammonium, there's our Ka, times our Kb. Our Kb is ammonium hydroxide ammonia. Ammonia cancels ammonia. Ammonium cancels ammonium. And you get H plus times OH minus, which is Kw. So this is important because You may not know Kb, but if you can find Ka for the conjugate acid, you can calculate Kb. You may not know Kb, but if you know Ka, you can calculate Kb. So the importance of this relationship is, again, for any conjugate acid-base pair, Ka times Kb is equal to Kw. That allows you then, if you know Ka, but you don't know Kb, you can calculate Kb. So for example, a question on quiz 2 may give you the Kb, but in fact you need Ka. So you're given, let's say on this problem, you're given Ka, but you read the problem and you go, wait a minute, I don't need Ka, I need Kb. No problem. Ka times Kb for a conjugate acid-base pair is Kw. So if you know Ka, you simply take Kw and divide it by Ka, and boom, there's the Kb that you need. So if you know Ka, you can calculate Kb. If you know Kb, you can calculate Ka for any conjugate acid-base pair. Right-to. Well, certainly are. Had a cup of coffee right before coming. All right, here's some fun stuff. Uh-oh. I lost both of my mics. Okay, here's some fun stuff. Where's my eraser? Ah, yeah. So it's fun to look at the hydrohalic acids. Hydrohalic acids. So let's take a look at the acids. I'm going to need 1, 2, 3, 4. Don't screw this up. Okay, so we're going to make a table. Acid. This is bond strength. Streng. In kilojoules per mole. And this is acid strength. So there's our table. So, our first member, we're talking about the hydrohalic acids. I don't know, my knee's giving out now. The hydrohalic acids, you can see them. Watch your head, please. They're right here, all the halides. Boom! 1 over. Let's try again. All the halides, you can see them right up there. Fluoride, chromide, bryodide. I don't think bryodide is one of them. Close enough. I could do this all day. They used to have a big one on the wall. It was much easier to hit. But you see them there. Here. Where's my laser pointer? We'll do it the preferred way, okay? Not as fun, I guess. But there they are. So you can stick a proton on all of those, and you make our friend HF. So what bond are we talking about? We're talking about that sigma bond between the hydrogen and fluoride. And that is 568 kilojoules per mole. And that is the only example in this bunch of a weak acid. Because we know our friend HCl, which slightly lower bond strength, but that one's strong. And we can take a look at our friend HBr, hydrobromic acid. Bond strength weaker still, also a strong acid. And then finally we get to hydroiodic acid, and weaker bond still, and that's also strong. Now, what's fun about this for me is, of course, to consider the random walk. It's what makes everything fun for me. So, we can think about it this way. Here's this HF molecule. It's got the strongest bond of the bunch, 568 kilojoules per mole. So let's say our aqueous solution, it's getting hammered on by randomly walking water molecules in the aqueous solution, but because it has the highest bond strength, very little of it gets broken in half to dissociate. You see what I mean? You got to break that bond to get it to dissociate, and at room temperature, the energy of the random walk is not enough to break that bond very much, and so it's a weak acid. But look at the just a little bit weaker bond, and now the randomly walking water molecules slam into that HCl and it falls apart, and it's a strong acid. So that little bitty difference in the bond strength makes a difference between, the Colonel saying molecules are like little hammers and they can pound other molecules into submission. Well, at room temperature, randomly walking water molecules can't pound HF into submission. It doesn't fall apart. At room temperature, randomly walking water molecules pound HCl into submission and it falls apart. So the energy excuse me. So the energy of the random walk can be very tunely fine. Oh, the other thing to think about is, what about the effective temperature?
Yeah, I was going to ask, is it a strong acid at higher temperatures?
If you lower the temperature, this becomes a weak acid. If you lower the temperature, this becomes a weak acid because, again, lowering the temperature means the little randomly walking water molecules can't hit the molecule HCl as hard. So at room temperature, we got the only example of this series that's weak is HF, and all the other ones are strong. And so that is something that we often what's that?
Does decreasing the temperature make them all weak?
Absolutely. You can lower the temperature enough such that every one of these will be a weak acid. I mean, you can lower the temperature enough such that the solution turns into ice, and that would change things. But yes, you could lower the temperature and all of those would become a weak acid. Okay, what else we got? Oh, I know. Where'd that go? Ah, there it is. Okay, so we got that. Okay, the other family of acids that's fun. Let's stop here. I'm tired. Let's pick this up on Wednesday. What?